In the heart of the Milky Way lurks a true cosmic monster, an object millions of times more massive than our Sun. Everything in our galaxy, including us, dances in a lazy, billion-year-long orbit around it. Its name is Sagittarius A star. For decades, astronomers have been mesmerized by the frantic trajectories of stars flying around this point. Every time, the mathematics led them to the same conclusion. There, in the darkness, sits a supermassive black hole. Even when the Event Horizon Telescope gave us that legendary donut photo in 2022, everyone finally exhaled. Well, it's proven, but there is one massive catch. It is still not 100% proven. Right now, fresh scientific papers are literally turning this established fairy tale upside down. What if Sagittarius A star is not a black hole at all? What if, at the center of the galaxy, there is a super dense core of pure dark matter? A core that smoothly transitions into a giant invisible cloud enveloping our entire star system. This hypothesis doesn't just challenge the scientific consensus, it strikes at the biggest question in modern physics. What on earth is this dark matter? Perhaps the answer has been right under our noses all along, in the very heart of our home. I'm Vlad, and this is VitoSpase. Today, we are breaking down a wild, yet damnably elegant theory that could bury our current understanding of the galactic center and bridge two of the universe's greatest mysteries. Let's dive in. The supermassive classic. About 27,000 light-years from Earth lies a point of no return, the center of the Milky Way. It is a place shrouded in such dense clouds of cosmic dust that looking at it directly with optical telescopes is simply impossible. The first hints reached us back in the 1930s. Carl Jansky picked up a strange, distinct radio signal coming from the direction of the constellation Sagittarius. Back then, nobody had any idea what it was. Black holes were still considered mere mathematical abstractions on Einstein's papers. Scientists argued until they were hoarse. Could it be a dense cluster of stars, or the remnants of a supernova? Only in 1974 did Bruce Balick and Robert Brown prove that one specific, incredibly compact object sat there. Brown later dubbed it Sagittarius A star. By that time, physicists had fine-tuned the theory of black holes, and the puzzle began to fit together. Rumors spread. It seemed a true titan was sitting at the center. In the 1990s, as technology advanced, astronomers were left speechless. They saw huge stars racing around an absolutely empty, dark point at insane speeds. To spin a star that fast, something millions of times heavier than the Sun must be locked in that spot. That became the primary piece of evidence. These stars close to the center were named S stars. Their orbits are now mapped to the millimeter. They move at speeds of up to 24,000 kilometers per second. That's about 8% of the speed of light. For example, the star S2 completes a full orbit in just 16 years. For comparison, it takes our Sun over 200 million years to circle the galaxy once. It was through the trajectories of these cosmic racers that scientists were able to calculate the mass of the hidden object. Researchers were awarded the Nobel Prize in Physics in 2020 for this titanic effort. An interlude on connection. The coolest thing about this discovery? It was a colossal international project. Scientists from all corners of the globe pooled data, argued on Zoom, and exchanged terabytes of code. They had to find common ground, despite different cultures and accents. It makes you think about how important it is to be able to communicate. Here at VitoSpase, we love digging into the secrets of the cosmos. But for those secrets to be revealed, people on Earth need to understand each other. Whether it's an international team of astrophysicists or you planning a trip to an epic space launch in French Guiana or the USA. As scientists calibrate their interferometers and we learn to understand universal scales, let's head back to where the laws of physics are bursting at the seams. The nuances of the Nobel. Two independent groups, led by Reinhard Genzel in Germany and Andrea Ghez in the USA, proved that Sagittarius A star weighs as much as 4.3 million of our suns. All this monstrous mass is compressed into a tiny spot with a diameter of only 24 million kilometers. It's so small that it would easily fit inside the orbit of Venus. They shared their Nobel Prize with Roger Penrose scenarios, who mathematically proved that black holes are an inevitable consequence of Einstein's theory of relativity. It would seem the case is closed. Sagittarius A star is a supermassive black hole. Case dismissed. But the devil, as always, is in the details. Do you know how the official Nobel Prize citation for Genzel and Gez read? For the discovery of a supermassive compact object at the center of our galaxy. An object. The phrase black hole was absent from the official verdict. That is because, despite the general consensus, it remains a hypothesis. Scientists continue to look for alternatives. Ideas involving star clusters were dismissed earlier, but other exotic scenarios remain on the table. For instance, boson stars made of subatomic particles, gravastars, or cores of pure dark matter. The birth paradox. Why even look for alternatives if the black hole theory works so well? It's simple. We have a massive, gaping hole in the theory itself. We have no idea how supermassive black holes are born. With regular stellar mass black holes, from a few up to 100,000 solar masses, everything is clear. There was a giant star, it ran out of fuel, exploded as a supernova, and its core collapsed under its own gravity. We've studied this process inside out. There are an estimated billion such stellar corpses in our galaxy alone. But Sagittarius A star is a completely different scale, 4.3 million solar masses. There are simply no stars in the universe that could leave such a remnant behind after a collapse. Plus, don't forget, you cannot see a black hole. It doesn't emit light, and anything that crosses the event horizon is gone forever. We only see its gravitational footprint on its surroundings. This ambiguity keeps the door open for other ideas, one of which made a loud statement in February 2026. The La Plata sensation, Valentina Zapata Torres and her colleagues at the Institute of Astrophysics of La Plata in Buenos Aires study dark matter on a galactic scale. They decided to conduct a rigorous mathematical experiment. They took an alternative model where, instead of a black hole, a super-dense clump of dark matter sits in the center, and overlaid it on real, multi-year observational data of the star S2 and 5 so-called G objects. G objects are strange things discovered in the 2000s. They act like stars but look like gas clouds. When they fly close to Sagittarius A star, they deform and stretch violently under gravity, then clump back together. They are likely stars wrapped in a thick cocoon of dust. Any alternative theory must perfectly explain this jelly-like behavior, and the team succeeded. The results, published in the monthly notices of the Royal Astronomical Society, were shocking. The model of a dense dark matter core was able to reproduce the orbits of stars and G objects with 99% accuracy compared to the standard black hole model. Do you realize what that means? With current observational data, you physically cannot distinguish a black hole from a clump of dark matter. Their gravitational fingerprint at that distance is identical. A quantum shield of dark fermions. But there is more. The model also solves another major secret of physics: what dark matter is made of. Recall that in the 1930s, Fritz Zwicky noticed that galaxies in the Coma cluster were moving at such speeds that they should have flown apart. Something invisible was holding them together. Later, this was confirmed. The edges of galaxies rotate too fast, as if held by an invisible giant. Today, it is believed that the Milky Way is surrounded by a giant, diffuse, spherical halo of this substance, accounting for 85% of all matter in the universe. But we don't know what it is. Physicists are looking for hypothetical particles, axions, WIMPs. The La Plata team offers their own candidate, dark fermions. Fermions are a class of particles, including the electrons and quarks we know, that obey the Pauli exclusion principle. Simply put, two identical particles cannot occupy the same quantum state in the same place. This is precisely why matter doesn't collapse into itself and why we don't fall through the floor. If dark fermions exist, they cannot be compressed infinitely either. They push back. Under extreme conditions, they create colossal internal quantum pressure. The result is an ultra-dense, stable cosmic sphere that can match a supermassive black hole in mass. Dr. Carlos Arguelles, the leader of the research group, explains, "Such a core looks indistinguishable from a black hole, but it lacks a singularity, a point of infinite density, and has no event horizon. And the most beautiful part, these fermions don't just stop abruptly. The dense core in the center transitions smoothly into a rarefied cloud that extends to the edges of the galaxy. This means Sagittarius A star and the Milky Way's dark matter halo aren't two separate objects, they are one continuous structure. No other theory offers such stunning unity. The mystery of the outskirts and red dots. This model unexpectedly solves another problem posed by the European Gaia telescope. In 2022, Gaia measured the velocities of 1 billion stars and discovered an oddity. At the very far edges of our galaxy, the rotation speed of stars drops sharply, the so-called Keplerian decline. Standard dark matter models cannot explain this decline. According to their logic, the speed shouldn't drop. But due to the Pauli exclusion principle, dark fermions form a halo with a very clear, almost perfect spherical boundary. And that is exactly where the star speed drops, which is what Gaia recorded. Moreover, this theory elegantly explains recent findings from the James Webb Space Telescope. Remember those mysterious little red dots in images of the early universe? These are objects with the mass of billions of suns that existed just 800 million years after the Big Bang. A classical black hole simply wouldn't have had time to consume enough matter in such a short period. But for dark fermions in the dense early universe, there was no need for progenitor stars. They could have collapsed directly into massive cores from primordial gas. How do we find the truth? Let's summarize. The orbits of S stars, the maneuvers of G objects, the anomalies found by Gaia, and even the famous black hole shadow silhouette. Everything is explained by the dark fermion model without a hitch. Does this mean black holes don't exist? No. The scientific consensus remains in favor of the classical black hole, but this alternative has proven it deserves to exist. How do we settle the debate? We need one key witness, the photon ring. A real black hole has such strong gravity that it forces light to orbit the event horizon, creating thin, bright rings before falling in. In a dark matter core, there is no event horizon. Light simply bends and continues on its path without getting stuck in infinite loops. To catch this ring, NASA is preparing the Black Hole Explorer (BHEX) mission, a space radio telescope that will connect with ground-based systems to create a virtual dish larger than Earth, though it likely won't launch for some time. For now, scientists are using the Gravity instrument in Chile to track tiny shifts in the S2 star's orbit, and in South Korea, physicists are trying to catch direct collisions between dark fermions and ordinary electrons in the NEON experiment. What fascinates me most about this story is the beauty of the solution. For nearly a century, we thought of the monster in the center of the galaxy and invisible dark matter as completely different things, but perhaps they are pieces of the same puzzle. What do you think? Are you ready to trade the good old black hole for a quantum sphere of dark matter? If you enjoy this kind of deep but accessible breakdown of the cosmos, subscribe to VitoSpase, hit the like button, and ring the bell. Your support helps the channel grow and create content that interests thinking people. Keep looking up. See you next time.